Swayam Prabha. Digital India. Educated India.
We are going to start with another potential applications of fuzzy sets, and that is in the form of fuzzy clustering. Now, this clustering is a powerful tool for data mining, and the purpose of data mining is to extract useful information from a data set. Now, actually what we do in clustering, the clustering is done based on the concept of similarity. That means, the two similar points should belong to the same cluster and two dissimilar points should belong to two different clusters. Now, if you see the literature, the clustering could be either crisp or fuzzy in nature. Now, for the crisp cluster, there should be well defined boundary, but for the fuzzy clusters, the boundaries could be vague. Now, let me take one very practical example, very simple example. Now, supposing that say you are staying in a hostel, and in the hostel there are say 1000 students. Now, if you see these 1000 students, they will move in a few clusters. They will form the clusters based on their similarity, and might be these 1000 students will move in say 10 or say 12 clusters. And you can see that, so a particular student may belong to so more than one clusters, and there is another possibility. So, a particular student may leave a cluster and he may join another cluster. So, these are all examples of actually the fuzzy clusters, and for each of the clusters there will be a leader, and that is nothing but the cluster centers. Now, if you see the literature on fuzzy clustering, we have got a large number of methods. For example, say we have got fuzzy C-means clustering. So, we have got the fuzzy C-means clustering, then we have got the potential based clustering, we have got entropy based clustering, and so on. So, there are a few other methods, but out of all the methods of fuzzy clustering, the fuzzy C-means algorithm is the most popular one, and we are going to discuss in detail the working principle of so this fuzzy C-means clustering. Now, if you see the fuzzy C-means clustering, so this technique was proposed in the year 1973 by Bejdek, and after that actually a lot of modifications has been incorporated into the fuzzy C-means algorithm. Now, here the way the clustering is done is as follows. Now, a particular data point, supposing that I have got a large number of data points and I have got a few predefined clusters. So, a particular data point may belong to different clusters with different numerical values of membership, and some of the membership function values will become equal to 1.0. Now, here if I consider say a particular data point and how much close is that particular data point with respect to the cluster center. So, what we do is like we try to measure the Euclidean distance between that particular data point and cluster, and the more the value for this Euclidean distance, the less will be the similarity and the more will be the dissimilarity, and our aim is to minimize this particular dissimilarity, so that the data point can be brought very near to the cluster and it may belong to the cluster. Now, this particular principle has been used mathematically just to design and develop the fuzzy C-means algorithm. Now, I am just going to discuss its principle in details, and after that I will be solving one numerical example just to make it more clear. Now, here I am just going to take a very typical example. Now, this example is as follows. Supposing that in higher dimensional space, say L dimensional space, say I have got a large number of data points, say capital N number of data points. Now, each data point is denoted by x I, where I varies from 1 to up to capital N, and our aim is to form the clusters, the fuzzy clusters of these particular data point based on their similarity. Now, if I consider, so e particular data point say x I, now this is in L dimension. So, to represent this particular point, I need to have the numerical values like x I 1, x I 2 and up to say x I L. So, I need to have so many numerical values if I want to represent e particular data point say x I in L dimension. Now, let us see how does it work, how does this particular the fuzzy C-means algorithm works. Now, I have already mentioned that to start with, so we will have to form a few clusters, that means there should be some predefined clusters. Now, let me take some predefined clusters like this. For example, say one fuzzy cluster could be something like this, another fuzzy clusters could be something like this, and there could be overlapping also, because these are all fuzzy clusters. Another fuzzy clusters could be say something like this, another fuzzy clusters could be something like this. Now, supposing that I have defined say 4 clusters initially, and I am just going to take the decision whether a particular data point, say this particular data point will belong to, whether it is belong to cluster 1 or cluster 2 or cluster 3, and let me consider the cluster 4 as a general cluster, say jth cluster say. So, this is nothing but the cluster J. So, there could be some other clusters also. Now, how to take the decision whether this particular data point, say the ith data point should belong to any one of these clusters or not. Now, how to proceed? Now, the way we actually try to solve the problem is as follows. So, what we do is, as I told, we try to find out the Euclidean distance between, so this data point and the cluster center, and that particular data, the Euclidean distance, as I told, the more the distance, the less will be the similarity and the more will be the dissimilarity, and our aim is to minimize, so this particular the dissimilarity. Now, if you see, say for the first cluster, supposing that I have got a cluster center here, and the second cluster, say cluster center is here, the third cluster, the cluster center could be here, the jth cluster, the cluster center could be here. And what we do is, so from here this ith point, so we try to find out like what should be the membership value, supposing that the membership function value between the ith data point and the first cluster center is nothing but mu I 1, that is the membership value between the ith data point and the first cluster. Similarly, the membership value between the second cluster and ith data point, so this is nothing but mu I 2. Similarly, between the third cluster and the data point, that is the ith data point, so mu is nothing but mu I say 3, and similarly so this particular between I and j, jth cluster, so the membership function value is your mu I j. So, mu indicates actually the membership function value, and which varies from like 0.0 to 1.0. So, this is the range for the mu, and here, so a particular condition has to be fulfilled, so that the sum of all the mu values becomes equal to 1.0. So, this is actually a functional constraint. Let me repeat. So, with respect to this particular I, and we have got different mu values with the different clusters, and the sum of all the mu values should be equal to 1.0, and that is nothing but the functional constraint. And what is our aim? Our aim is to find out the fuzzy clusters. Now, let us see how do we proceed. Now, to proceed further, so what I will have to do is, I will have to formulate as an optimization problem, and this particular optimization problem has to be solved using some technique. Now, what I do is, we try to minimize the dissimilarity as I mentioned, and this particular dissimilarity will be expressed in terms of the Euclidean distance value, that is nothing but is your dij square. Now, what is dij? Dij is nothing but the Euclidean distance between the ith data point and your ith data point and jth cluster. So, this is the Euclidean distance. Now, so what is our aim? Our aim is to minimize the dissimilarity, that means I will have to minimize. So, dij square, and it is multiplied by, so mu ij g. Now, what is mu ij? Mu ij is nothing but the membership function value between the ith data point and jth cluster sensor. Let me repeat, mu ij stands for the membership function value for ith data point with respect to the jth cluster center, and here we put mu ij raised to the power g, and this particular g is nothing but the level of your the fuzziness. Now, if you remember that we discussed the power of a fuzzy set. So, this is almost similar to the power of the fuzzy set. So, this g is nothing but the level of cluster fuzziness, and generally we consider g is greater than 1. Okay. Now, let us see how to write down this objective function. Now, our aim is to minimize the dissimilarity, and that is if mu comma c, mu is the membership function value, and this particular c actually it indicates the total number of clusters or the number of clusters to be made, and c has got a range. For example, say c should be greater than equals to 2 and it should be less than equals to n. What does it mean? It means that the minimum number of clusters should be 2, it cannot be 1. If it is 1, then no clustering is done, and this the maximum number of clusters cannot exceed n, that is the total number of data points. So, c is nothing but the number of clusters. So, this if mu comma c is nothing but summation j equals to 1 to c, summation I equals to 1 to n, mu I j raised to the power g d I j square. So, this is the objective function which I will have to minimize, subject to the condition that summation j equals to 1 to c mu I j is equals to 1.0, and this is nothing but the functional constraint. Now, let us see how to solve it using the traditional method of optimization, and to solve this type of problem we take the help of Lagrange multiplier. So, what we do is, so this objective function, so this is written in a slightly different form, and that is nothing but your f bar mu comma c comma lambda 1 lambda 2 up to lambda n, and this is nothing but summation j equals to 1 to c, summation I equals to 1 to n, and I will have to write the expression for the objective function, that is mu I j raised to the power g d I j square, and we add this particular thing corresponding to the functional constraint, that is summation I equals to 1 to n lambda I, then comes summation j equals to 1 to c mu I j minus 1. So, this is actually the functional constant. So, this 1 you bring it to the left hand side. So, I will be getting this particular the expression, and here. So, this particular lambda I is nothing but is your Lagrange multiplier. So, this is nothing but is your Lagrange multiplier. Now, I have got only one big expression for this objective function, and I will have to solve using the method of calculus. Now, what we do is we try to find out the derivative of f prime with respect to mu, the total derivative, and put equals to 0. Then the derivative of this f prime with respect to c, put equals to 0. Then derivative of f bar with respect to your Lagrange multiplier lambda 1, put equals to 0. Then we write with respect to lambda 2, and the last is your. So, d f bar d lambda n, and you put equals to 0. Now, if we put all such things equals to 0, so you will be getting a set of equations, and those equations if you solve, then there is a possibility that you will be getting actually the expression like your the C C j is nothing but the cluster center corresponding to the jth cluster. So, what should be the expression for the cluster center? Now, this C C j is the jth cluster center. So, this will become your summation I equals to 1 to n mu I j raised to the power g x I divided by summation I equals to 1 to n mu I j raised to the power g. So, this is actually is going to give the coordinate of the jth cluster center. Now, the jth cluster center, now as the data are in L dimension, so it will have L numerical values, and accordingly I can write down like your C C j k. Now, k varies from 1 to L. So, I can find out the information for each of the dimension of this particular the cluster center. And another expression you will be getting by solving those set of equations, that is nothing but mu I j, that is the membership value of the ith data point with the jth cluster center, and that is nothing but 1 divided by summation m equals to 1 to c d I j divided by d I m raised to the power 2 divided by g minus 1. So, if we solve those equations, we will be getting these two particular the expression. One is actually how to determine the coordinate of the cluster center, and another is how to determine the membership value of a particular data point with respect to a cluster, say jth cluster, and what is our m. So, in this algorithm what we do is we try to update the cluster center and the membership value of the data points with respect to the cluster center iteratively. So, this is actually an iterative process. So, this algorithm is an iterative algorithm. So, this I have already mentioned. Now, I am just going to tell you the steps of this Fuzzy-Simmons algorithm, like the FCM algorithm. So, one after another. Now, the step 1, we assume the number of clusters to be made, and supposing that is denoted by C, and as I have already discussed, the C is greater than equals to 2 and less than equals to n. Now, step 2, we select some appropriate level for cluster fuzziness, and so this is nothing but G. Generally, it is considered G is greater than 1. For example, it could be say 1.25, 1.5 and so on. Then step 3, so this mu I j, that is the membership value of the ith data point with the jth cluster center. So, what I do is we try to initialize at random, and then we try to modify it through a large number of iterations. Now, if there are n such data points, so capital N number of data points, and if we are generating say the C number of clusters. So, for each data point I should have C number of numerical values, C number of numerical values for the membership, and I have got n number of data points. So, the size of the initial membership matrix, that is mu, it will have the dimension like n cross C, where capital N is the total number of data points and C is the total number of predefined clusters. So, I will have to generate initially the membership matrix mu at random, and what is the size of that particular matrix, that is n cross C. Now, this I have already mentioned that mu varies from 0 to 1, and the sum of all the mu values corresponding to a particular point is nothing but 1.0. So, this is the way actually the algorithm is working. Now, then we go for step 4. Now, here actually what we do is we try to update the cluster center, that is your the kth dimension of the jth cluster center, like CCJK is nothing but the kth dimension of the jth cluster center, CC. So, CCJK is nothing but summation I equals to 1 to n mu I j raised to the power g x I k, k indicates actually the dimension, divided by summation I equals to 1 to n mu I j raised to the power g. So, this is the way actually we can calculate the kth dimension of the jth cluster center. Now, step 5, we calculate the Euclidean distance between the ith data point and jth cluster center, and that is nothing but is your d I j. Then step 6, we try to update the membership value of the ith data point with respect to the jth cluster center, that is your mu I j. Now, this mu I j is nothing but 1 divided by summation m equals to 1 to C, C is the total number of clusters, d I j divided by d I m raised to the power 2 divided by g minus 1, if d I j is found to be greater than 0. And if d I j is found to be 0, then what happens? The distance between the 2 points is 0, that means the similarity is the maximum, and your mu I j will become equal to 1.0. Now, step 7, we repeat from step 4 to step 6 unless the change in mu values come out to be less than some pre-specified value, say it is denoted by epsilon. Supposing that epsilon is say 0.001, a very small value. Now, I am running this particular algorithm. Now, after running this particular algorithm through a large number of iteration, there is a possibility that the mu values are going to reach some saturated level, and after that there may not be any significant change in the values of this particular the mu. And if this particular change is found to be less than equals to this, then we say that the algorithm has reached the optimal solutions, and we try to terminate the program. So, this is the way actually we terminate that particular the program. So, this shows actually this algorithm the steps for this particular the algorithm. Now, here I just want to make one comment. Now, this algorithm is an iterative algorithm. Now, as it is an iterative algorithm, there is a possibility that the quality of the clusters will be updated and iteration wise, and there is a possibility that as the algorithm runs, we will be getting more and more the compact clusters. Now, I am just going to define what do you mean by a compact cluster, and there is another adjective which is very frequently used, that is the distinctness of the clusters. Now, here I am just going to define what do you mean by the compactness of a particular cluster. So, the compactness of a cluster, and another is your distinctness of a particular the cluster. Now, let me try to define what do you mean by the compactness of a particular cluster. Now, supposing that I have got say one fuzzy cluster something like this, okay, and say I have got a cluster center. Supposing that the cluster center is denoted by, for this J is denoted by say C j. Now, here surrounding this particular jth cluster, there will be a large number of members who are following actually the cluster center. Okay. Now, what we do is we try to find out the Euclidean distance between the cluster center and all the points surrounding it. For example, say here there are 200 points surrounding the cluster center. So, what we do is we try to find out the Euclidean distance between the jth cluster center and each of these particular the 200 data points surrounding that cluster center. So, how many Euclidean distance values we will be getting? We will be getting 200 Euclidean distance values, and what you do is you add them up and you find out the average. Now, if the average Euclidean distance is less, we define that this particular cluster is a very compact cluster. So, this is the way actually we define the compactness of a particular cluster. Now, let us try to define the distinctness. Now, supposing that say I have got a large number of data points and we have got a few fuzzy clusters. For example, say one cluster could be something like this. So, this is the first cluster and its center is your C 1. I have got another fuzzy cluster something like this, and supposing that so its cluster is C 2. Then I have got another, say might be I am here. So, I will be getting another cluster say C 3. I have got another cluster here and this is nothing but the cluster center is say C 4 and so on. So, what we do is we try to find out the Euclidean distance between the cluster centers. For example, we try to find out the Euclidean distance between C 1 and C 2, then comes C 1 and C 3, then comes C 1 and C 4. We also try to find out what is the Euclidean distance between C 3 and C 4, C 3 and C 2, and C 3 C 1 I have already calculated. Then we try to find out what should be the Euclidean distance between your 2 and 4 and so on. So, all the Euclidean distance values between the two possible clusters we determine, and we try to find out what should be the average value. Now, if the average Euclidean distance between the cluster centers, if it is found to be more, then we declare that this is a very distinct cluster. Now, if you use this fuzzy Siemens algorithm, so there is a possibility that you will be getting a very compact cluster, but at the cost of distinctness. So, you may not get a very distinct cluster using this particular the fuzzy Siemens algorithm. But what is our aim? Our aim is to get more compact as well as more distinct cluster. How to get it? So, that I am going to discuss after some time. So, these are actually the relative merits and demerits of fuzzy Siemens algorithm. Thank you.